Okay. Okay, the last class we discussed about uniform continuous. Okay, today we are going to start differentiation. Okay, differentiation of a function at a point. Okay. So first definition: differentiation or differentiability of a function. Differentiability of functions. Okay, so definition: suppose we have an interval j and f is a function from j to r. Definition: so let j is a subset of r, be an interval, and we fix some c in j. So c in j, and we have take function let f is a function from j to r, be a function. Then we say f is differentiable at c. Then f is said to be differentiable at c. Differentiable at the point c if the limit exists. That is, if there exists a real number alpha in R such that the limit x goes to c, this function f of x minus f of c by x minus c. If the limit exists, and then we call the limit is alpha. Okay, such an alpha exists, and we say that f is differentiable, and we denote this alpha by f dash of c. If the limit exists, the limit is denoted by f dash of c. Okay, so the limit should be exist. Already we know that how to find the limit of a function. Okay, we have to find the right hand limit, left hand limit. Both are equal, then the limit exists. Okay. Now, geometrically says, so given any point, it has a unique tangent to that point. Okay. So geometrically, what do you mean by differentiability? Suppose we have a function. Okay. Suppose simply we draw some function. Suppose this is our function f of x. So we are talking about the derivative of f point. Okay, suppose this is domain, we take some point c. Okay. So otherwise we can rewrite this, the denominator x minus c is we call some number, and then we rewrite, first we rewrite this function. Okay, so we call this h equal to x minus c. Okay, therefore what is c? Sorry, what is x? X is equal to c plus h. Okay, so x is nothing but c plus h. We call this h equal to x minus c. Therefore, this becomes limit x goes to c is nothing but h goes to 0. Because take x minus c goes to 0, but x minus c we call h. Therefore, limit h goes to 0. F of what is x? C plus h minus f of c by h. If the limit exists, then we say the function is differentiable at a point c. Now, suppose we take some point c. So we are looking about the derivative of the point. So geometrically, so c plus h, suppose we take something here or here depending upon h. Okay, here the c is h is positive or negative. Okay, suppose we have c plus h is here. So for this c corresponding, we have a point on the curve. This is f of c. Again, for this we have corresponding point on the graph is f of c plus h. Okay, now so what here is saying that, so what is the difference between these? C plus h minus c, that is c. Okay, now this point, this c plus h approaches to c. Okay, that means what? H approaches to 0. So h approaches to 0 same as this point moves towards the c. Therefore, this point corresponding to the point is moves to this point. Okay, therefore you will get a tangent, unique tangent to that point. So when we say a function is differentiable at c geometrically, it has a unique tangent at that point. Suppose that point have a more than one tangent, the function is not differentiable at that point. Okay, so we will discuss some example. Suppose whenever the function have a corner point, suppose look at the mod x graph. Okay, so we know that how mod x graph look like some V shape. Okay, sorry. So assume that this is mod x graph. Now this mod x graph in the point 0, at the point 0, so we can draw more than one tangent. So if you take this x-axis, touches exactly that point 0 is one of the tangent line, or you can draw the line touches only that point, that is another tangent. If you draw another line like this also touches exactly that point, but is also tangent. Therefore, the function at the point 0, it has more than one tangent. Therefore, mod x is not differentiable at the point 0. Okay, so suppose a function have some corner point. So corner means some edge like this. So this point, the function is not differentiable. So suppose a function like this, so it's not differentiable at this point, and this point, all the points, because we can draw more than one tangent at that points. Okay, so this geometrically say a function is differentiable or not. It has a unique tangent, and then the function is differentiable at a point. So when we say it's differentiable on the set, it is differentiable at every point on the set. We say f is differentiable on the set. Okay, so therefore mod x is not differentiable only at x equal to 0. Suppose you can move this mod x graph to here. Suppose like suppose the graph look like this. So maybe I take this point. Actually, this is nothing but mod x minus 1 graph. This is x minus 0. Just I take this point to here and then draw the graph. This is actually a modulus of x minus 1. Again, we have a sharp corner at the point x y equal to 1, right? So sorry, I think this is not a graph mod x. This is actually 0. If substitute x equal to 0, we'll get an okay. Sorry, this is not a graph. Actually, mod x graph. Oh, sorry. Sorry, once again I will share. Please wait.
Sir, that is mod x plus 1, sir.
Yeah, mod x plus, mod x plus 1, that's one. So please wait. So therefore, whenever modulus of something, you have to solve that inside that you can get the x value. At that point, the function is not differentiable. Okay. Okay. So I think I lost that what I wrote. So once again I will write. So I lost the definition. So okay. So quickly I can write. So when we say a function is said to be differentiable at the point, the limit exists. So limit x goes to c, f of x minus f of c by x minus c. Okay. So if it is exist, and suppose we denote the limit is f dash of c. Okay. So geometrically we can say, suppose we have a point, we have a function f like this, and we have a point x here, and if we take some point c here, so we are talking about differentiability at the point c. Therefore, suppose this x approaches to this side, or suppose if we take x here, suppose x approaches to this side. Okay, there are two ways to approach c, either from the left or right. So both the limit exist and should be same, then we do not this f dash of c. Okay. So algebraically say, geometrically says that it has a unique tangent. So you'll get a unique tangent at the point C. It touches exactly one point. Okay. So you are not allowed to draw this. This is not tangent. Okay. So you have to draw the tangent like this. So if you had a unique tangent, we say it's differentiable. Okay. Otherwise, suppose a function have some corner, then the function is not differentiable at that point. Okay. Okay. So this is a definition, algebraic geometric definition of differentiability. Now we discuss some examples. Already we know that every constant function is differentiable at any point. So exercise, the first one is f is a function from J to R defined by f of x equal to c. C is some fixed number for every x in the domain J. Then f is differentiable at any point. Okay, suppose I take some other constant a. So f is differentiable to c. Why? So we have to find f of x or c plus h. So if we fix some point c in j, we are talking about we are looking the function is differentiable at c or not. So that is we have to check the limit h goes to 0, f of c plus h minus f of c by h, if the limit exists or not. So this is about limit h goes to 0. F of c plus h is nothing but again a, because f is a constant function. Everything takes to 0. Therefore, this is 0. So therefore, limit exists and the limit is denoted by f dash of c. Therefore, is differentiable. Therefore, f is differentiable at the point c, and the value of the derivative at the point c is the 0. So we take the arbitrary point c, therefore f is differentiable on j, and then the derivative is always 0. Okay, this is a simple one. So we know the epsilon delta definition for this limit also, right? So we can use that also. Okay. So next example, if you take any linear function, so f is a function from j to r defined by f of x equal to ax plus b, where a, b are some fixed number in R. Now, if we take some arbitrary point C in J, we have to check the function is differentiable at C or not. So that means you have to find a limit. Limit h goes to 0, f of C plus h minus f of C by h. So this is equal to limit h goes to 0. F of C plus h is nothing but a into C plus h plus b minus of f of c is nothing but ac plus b whole divided by h. So this is equal to limit h goes to 0. If you multiply a inside, we have ac plus ah plus b and minus ac minus b by h. So AC cancel and BB cancel, HH cancel, because we get AH by H, therefore HH cancel, we get A. So if H goes to 0, we get E. So the limit exists and the limit is A. Therefore, f dash of C is A. And f is differentiable at C. So f is differentiable at C and the derivative of the point is A. So if we take it similarly, we can extend to this x power n. So the derivative of x power n is n into x power n minus 1. Suppose f of x equal to x power n, the derivative of the function at any point is n into x power n minus 1. So we have to find f of c plus h minus f of c. We have to use the binomial theorem, and then we can easily find this one. So why? So first you have to find f of c plus h minus f of c, and then you have to divide by h and then take the limit h goes to 0. So what is f of c plus h is nothing but c plus h whole power n. C per h power n minus f of c nothing but c power n. Okay, now expand this using the binomial theorem. We get a c power n plus nc1 c power n minus 1 into h plus nc2 c power n minus 2 into h square and so on. Finally, we get h power n minus c power n. Okay, this c power n cancel. Okay, so all the terms, look at all the terms have h. Okay, therefore we have n choose one value is nothing but n c power n minus 1 into h. Okay, and then the next one is n choose 2 c power n minus 2 into h square and so on. Finally, we have h power n. Now take divided by h. So what is f of c plus h minus f of c whole divided by h. So the first term h cancel, we have n into c power n minus 1 plus n choose 2 c power n minus 2 into h, because 1 h is cancelled, etc. plus h power n minus 2. Now if you take limit h goes to 0, limit h goes to 0, f of c plus h minus f of c is by h is, so only we get n into c power n minus 1, because all other terms contains h. If h goes to 0, this term goes 0, therefore we get. So limit exists, that limit is n into c power n minus 1. Therefore, the derivative of the point c is n into c power n minus 1. So in general, f dash of x is n into x power n minus 1. So similarly, we can find all the things. Okay, so we have some theorem to find the derivative. What is the derivative of this thing? Theorem. Suppose f is a function from j to r be given, be a function. Given, then f is differentiable at c. Then f is differentiable at c in j, actually c in j if and only if there exists another function, there exists another function f1 from j to r satisfying the following condition. Satisfying the following conditions. So the first condition is, we can write f of x as equal to f of c into f of c plus f1 of x into x minus c. Suppose if you write f of x equal to f of c plus f1 of x into x minus c for all x in j. Okay, and that f1 should be continuous at the point c. That f1 is continuous at c. If such a function f1 exists satisfying these two conditions, then we say that f is differentiable. If f is differentiable, then there is a f1 exists satisfying these two conditions. Now in that case, this f1 is nothing but the derivative of the function. Okay, so in such a case, what is the derivative of the function is nothing but this f1 of c. Okay, so if f of x is equal to f of c plus f1 of x into x minus c, and f1 is continuous at c, then that f1 is the derivative of the function. Okay, now we solve some problem related to this theorem. So what is the derivative of 1 by x? Okay, exercise. Suppose f of x defined to be 1 by x for x non-zero. Okay, now we are going to check about the derivative of any non-zero point. Okay, so therefore, first you got to find what is f of x minus f of c. Okay, so f of x minus f of c, what is f of x minus f of c? F of x minus f of c is f of x minus f of c. Okay, so f of x minus f of c is f of x minus f of c. Okay, so therefore first you got to find what is f of x minus f of c. f of x minus f of c is nothing but 1 by x, that is f of x. 1 by c is the f of c. So you got to simplify. In the denominator we have x into c, in the numerator we have c minus x. Anyway, we can take minus outside, we get minus 1 by c times x into x minus c. Okay. Now what is f of x? Take this f of c that side. We have f of x equal to f of c minus 1 by c times x into x minus c. Therefore, what is our f1 of x here? Minus 1 by c times x. So this is a continuous for all x non-zero. So such a f1 exists. Therefore, what is the derivative of the function at a point c? You have to substitute x equal to c. Okay. So therefore, minus 1 by c square, because already we have c, therefore this one. Therefore, in general, what is the derivative of any point is nothing but minus 1 by x square. Derivative of 1 by x is nothing but minus 1 by x square. Because our f1 is this and this continuous and satisfy this condition, therefore f is differentiable, that the value is 1 by c square. Okay. Now similarly, we can any function, if you write this format f of x equal to f of c plus f1 of x into x minus c, then that f1 is the derivative of the function. Okay. This theorem is very useful to find what is the derivative of your function. Okay, so the next theorem is, if it is differentiable, then it should be continuous. So every differential function is continuous, but continuous function need not be differentiable. So example is mod x. Mod x is a continuous function, but is not differentiable at the point 0. Okay, so what the theorem? Suppose if f is differentiable at c, then it is continuous at c. If f is differentiable at c, then f is continuous at c. F is continuous at c. The proof is simple. Okay, so the continuous at c means what we have to show? Limit x goes to c, f of x equal to f of c. We have to prove. Okay, we can simply we can write. So since it is okay, maybe I give the proof. So what is the proof of this? So given that f is differentiable at c, therefore by theorem this f of x can be written as some f of c plus some f1 of x into x minus c. Okay, now take limit x goes to c, f of x. So since f of c is independent of x, therefore we have f of c plus limit of this goes to 0. Therefore this should be 0. We get f of c. Okay. So limit x goes to c, f of x equal to f of c. Therefore f is continuous at c. Okay, because limit x goes to c, this value is 0. We don't know about this value, but the actually f1 of c, these are because f1 is continuous, but we get here f1 of c, but x goes to 0, this goes to 0. Therefore 0 into anything 0. Okay, so therefore every differential function is continuous, but continuous need not be differentiable. The example is mod x, because we get a sharp corner in the graph of mod x. We simply say it's not differentiable. Otherwise, we can say that limit not exist at the point x. So maybe we will prove it. So if you consider the function f of x equal to mod x, okay, now this f is not differentiable at 0. So then we have to find what is f of x minus f of 0. So f of x is nothing but mod x. F of 0 is mod 0, that is nothing but 0. Now we have to find that quotient f of x minus 0 by x. So this is nothing but x. And you find the limit x goes to 0, mod x by x. Already we know that this does not exist, because you get plus 1 and then minus 1. Right hand limit you get a plus 1, left hand limit you get minus 1, right? So therefore you should not get a unique value, therefore does not exist. So at the point 0, f is not differentiable because the limit not exist. Therefore, f is not differentiable only at 0 and differentiable at any other points. Okay. So therefore, this is a continuous function, but mod x is a continuous function, but not differentiable. Now the algebra of differentiability. Sum of two differential functions is differentiable function. Subtraction of two differential functions is differentiable product. And then composition of two differential functions is differential function. Okay, we state the theorem. Algebra of differentiability. Algebra of differentiable function. Suppose we have a functions f and g defined on j to r, be differential function. Both are differentiable at the same point c in j. Now the sum is differentiable. The first one is f plus g is differentiable at the point c, and what is the derivative of that point of the function is sum of the derivatives f dash of c plus g dash of c. Okay. Now if we take any scalar alpha from the real alpha in R, then alpha times f is also differentiable at c. Not alpha into c, just c. And what is the derivative of the function alpha into x, alpha into c at the point c is nothing but alpha times f dash of c. Okay. Now the third one is product. So therefore f into g is differentiable at c. And what is the derivative of the product of the function? Derivative of the product of function at the point c is nothing but you got to apply udv method. So that is first you have to fix f of c and then derivative g, that is g dash of c, and then fix g of c and then differentiate f, therefore f dash of c. So this is not term by term product, but the product is term by term product, but the derivative is you got to apply the udv. So you got to fix one and then differentiate other. Okay. And then the next one is quotient. Suppose f is non-zero and f dash of c, f of c is, we assume that f of c is non-zero and f is differentiable, then the 1 by f is differentiable at c. Then what is the derivative of this 1 by f? The point c is nothing but minus f of c whole square into f dash of c. That is u by v, but I am taking 1 by c, 1 by f. We can apply uv method, u by v. Okay, so similarly for chain rule says, suppose composition of two differential function is differentiable at c. We already discussed, I think so. Okay, anyway. So we discuss about the continuity of this, but what is the derivative of the composition of two function? Okay, so that is g composition f of at the point c is nothing but g dash of f of c into f dash of c, where f is differentiable at c, f is differentiable at the point c, g is differentiable at f of c, then the g composition f is differentiable at c. So that is a chain rule, and then the derivative is nothing but f dash of f of c into f dash of c. Okay. Okay, now there are some standard example. It's asked in the NBHM. Maybe I can write here. Example. Suppose f is a function from R to R is differentiable. R to R, be differentiable function. Be differentiable. at any point. And if we take n is a natural number and fix some real number a in R. Now find the limit. Find limit x goes to a power n into f of x minus x power n into f of x by x minus a. How to find the limit? Okay, we are going to split that. You have to add and subtract something in the numerator, and then you have to split into two function. Okay, so what is the solution? So how to split it? So first you have to consider x power a power n into f of x minus x power n into f of x. Now what can you add? Can add. So a power n into f of x. Just I'm adding, subtracting a power n f of a, and just I am subtracting this. Therefore, I am adding a power n f of a. Correct? And then what is the remaining thing? Plus x power n f of x. Okay, then otherwise I can. Yeah, correct. Now we can take f of a power n from the first two term. We get f of x minus f of a plus from these two term you cannot take anything outside, right? Therefore, if possible, okay, correct. So now we take new function g. So g of x I am going to divide x power n into f of x. Okay. Now therefore this is nothing but g of a plus this is nothing but g of x. Correct? Got it or not? Because I call this function is g of x. Therefore this is nothing but g of a. Now we get g of x minus g of y, but we need a minus term. Okay, no problem. I can take, if you take minus outside, okay. Now what you'll get a power n f of x minus f of a. So if you want, you can divide by x minus a. Therefore a power n f of x minus x power n f of x by x minus a. So we have to divide by x minus a each term. So if we take our g of x plus g of a. No, I think I have to add one more term. What the term I am missing? So actually my function itself is wrong. So I'm writing it's wrong. So sorry. So actually this is f of e. Sorry. So therefore this is, that's why I'm thinking why it's getting wrong. Okay, sorry. So this is f of a. So therefore now we can add this a power n into r. Okay, otherwise you can add x power n into f of a and then subtract. Okay, therefore x power n into f of a. So better sorry, a power n f of a. Okay, again we get some confusion. Better we can add x power n f of x. And then, okay, anyway, we got some more. Okay, actually, so just the idea is we have to add and subtract something. We can get a power n into f dash of, we will get x. And I think the other thing we'll get a g of x, the derivative of g of x. Okay. So anyway, I will work it out and then we will discuss in the next class this problem. Okay. So it takes some time. So just some small idea. We have to add and subtract some quantity. Okay. Anyway, I will see later. Okay. Now, almost we define what is the derivative of the function at a point. Now the important theorems, mean value theorem. So the theorem is actually called the mean value theorem. It's very important theorem. Mean value theorem. So in the continuous portion, we define the intermediate value theorem. For the derivative portion, there are some theorems, mean value theorem. So what is the mean value theorem says? Okay. And then maybe before go to mean values theorem, the important thing is Rolle's theorem. And then the corollary of the Rolle's theorem is that mean value theorem. So anyway, just I state what is mean value theorem. Suppose we have a function, continuous function from closed interval a comma b to r. B such that first the f is continuous on f is continuous on the interval closed interval a comma b, but differentiable on open interval a comma b. That is very important thing. So f is differentiable on open interval a comma b. This is second point. Third one is, okay, no third one, so only second. For Rolle's theorem we have one more condition, but for mean value theorem only these two conditions. If I have satisfied, then there exists C in open interval a comma b such that f of b minus f of a is f dash of c into b minus a. So that is a mean value theorem. So f of b minus f of c equal to f dash of c for some c in open interval a comma b into b minus a. So the f should satisfy, f should be continuous on closed interval a comma b, differentiable on open interval a comma b, then always c exists, satisfying the condition f of b minus f of a by b minus a equal to f dash of c. You can divide the b minus a both sides, we'll get this thing. Okay, this is a mean value theorem. So the corollary of the mean value theorem is Rolle's theorem. Rolle's theorem. These two theorems are very important theorem. So same condition, the only extra condition you have to assume that this f of a equal to f of b. Okay. So what the theorem says, again, f is a function from closed interval a comma b to r. B such that is satisfied. First one is f is continuous on the closed interval a comma b and differentiable on open interval a comma b. F is differentiable on open interval a comma b, and third one is that f of a equal to f of b. Both the endpoints maps to the same value, then there exists c such that f dash of c equal to 0. So then there exists c in open interval a comma b such that f dash of c equal to 0. So the Rolle's theorem says the root of this derivative of the function, that is f dash of c equal to means 0 means what? C is the root of f dash of c. Sorry, f dash. Okay, so the Rolle's theorem guarantee that the root of the derivative of the function. So these two theorems are very important. Okay. Now we saw some applications of this mean value theorem, MVT. Okay. So, okay. What are the applications? Exercise. Suppose a function is derivative is 0 for all points. Okay. So that is f is a function from j to r, be differentiable. This is a differential function with the derivative of the function is 0 for all points in the interval. Then f should be constant. F is constant. That is one application. So when we say a function is constant, every point in the domain maps to the same point. That is f of x equal to f of y for any xy. Okay, or any two different elements maps to the same thing. That is a constant function. So what we have to prove, f of, if it takes some 2 point, okay. So let x comma y or some a comma b. You can take any point in the interval j. J is any interval, we don't know, but any closed interval, or maybe you can R if you take the real entire space. Now what we want to prove? We have to prove that f of a equal to f of b. Okay. Because if we take any to a point, the image is the same, then means what? Everything maps to the same point. So now consider this interval. Anyway, j is some bigger interval. This is j. Now we take 2 point a, b inside this j. So consider this closed interval a comma b. Now restrict the function to this subinterval. Okay. So that we have to restrict the function f to see this subinterval. Again, that function is differentiable. Because the function differentiable in the bigger space, then it is differentiable in the smaller space, in the interval. Okay. Now apply mean value theorem to this function. Now what you'll get? It's differentiable and then it's continuous. Therefore, there exists c in open interval a comma b such that f of b minus f of a equal to f dash of c into b minus a. Now f dash of anything is 0. Therefore, this side is 0. Therefore, take this f of a to that side, we get f of a equal to f of b. Okay. So if you take any two arbitrary point in j, it maps to the same value. That means what? The function should be constant function. So this is a main application of mean value theorem. If suppose the derivative of the function is 0 for all points, the function should be constant function. Okay. But again, I assume that this j should be an interval, but it's in any interval. Okay. Either open interval or closed interval, but it should be an interval. Okay. Another application of this mean value theorem is, suppose the derivative of the function is positive for all points, then the function is increasing function. So we check a function is increasing or not. First you take the derivative. If the derivative is positive for all points, then we say is increasing. Okay, that is the second application of this thing. Suppose f is a function from j to r, is differential function at any point with the derivative is always positive, with f dash of x strictly greater than 0 for all x in j, then f is increasing. Then f is increasing function. So to prove f is increasing, what we have to do? If you take any two point x comma y, which are a comma b, a is less than b, then we have to prove that f of a less than f of b. That is increasing. Okay. So we start with the arbitrary point a, b. So let a comma b in j with A is less than B. Okay. What we have to prove? We have to prove f of A is less than f of B. Okay. Now, that is our aim. Now, anyway, now consider this interval, closed interval A comma B. This is subset of J anyway. So, since f is a differential function on J, but f is differentiable on closed interval A comma B, therefore is continuous. Therefore, now apply mean value theorem to this thing. What you will get? F of B minus f of A equal to f dash of C for some C into B minus A. For some C in open interval A comma B by mean value theorem. Now derivate, so this actually length of the interval, B minus A is length of the interval, is always positive. And in the assumption given, the derivative of all the points, if you take any points, always 0, greater than 0. Therefore, this is positive, therefore the product is positive, therefore we get this is positive. That is f of B minus f of A is positive. We can take f of A that side, we get therefore f of A is smaller than f of B. Therefore, we start with A less than B. Now we prove that f of A is less than f of B. Therefore, f is increasing function. Similarly, suppose the derivative is negative for all points, then f is decreasing function. So these are all applications of mean value theorem. Okay. Now, there are a lot of things are there. And then the inverse function theorem. Maybe I already mentioned that a continuous case, what is a inverse function theorem? For differentiability also, we have a inverse function theorem. So when this inverse of the function is differentiable, okay, when this inverse exists and when it is differentiable. So already we studied this inverse function theorem for continuous case. Now for differentiability case theorem, inverse function theorem. When the inverse of function is differentiable, okay, that is the thing. Okay, so what the theorem says, suppose f is a function from I to R, where I is an, if you take open interval A comma B to R, be continuously differentiable. Continuously differentiable function. So continuously differentiable means what? F is differentiable, the derivative exists, f dash exists, and then the f dash also continuous. That is the meaning of continuously differentiable, means what? F dash exists and then the f dash is also continuous. So continuously differentiable with the derivative is non-zero. So the derivative of any point x is non-zero for all x in the interval I. Then first thing, f is strictly monotone, either increasing or decreasing, because non-zero means are either positive or negative, right? Therefore, f is strictly monotone. That is the first thing, f is strictly monotone. Now the second thing is the image of the interval is some j, that is f of I. Suppose if j, where j is an interval, so continue the image of I is an interval. And then the third one is the inverse. We can define the inverse G inverse. Okay. So G is nothing but F inverse. So G is nothing but we call F inverse is continuous and particularly is differentiable function. Differentiable on the interval J. Okay. So J is nothing but F of I. Okay. And what is the derivative of this inverse? That is, what is the G dash of X? Is nothing but G dash of F of X equal to 1 by F dash of X. This is nothing but 1 by F dash of G of Y for all X equal to G of Y. in closed interval a comma b. So if you have any continuously differential function, if the derivative is non-zero, then that function is strictly monotone, and then the image of an interval is an interval. Then we can talk about the inverse of the function. We call g is the inverse of f. That inverse also differentiable, and then the derivative is nothing but 1 by f dash of x, where x is nothing but g of y. Okay. Because we can talk about differentiable, so because the domain of f is the domain of g is j. Okay, but if you take any point some y in j, but j equal to f of y, therefore this y is of the form f of something, I call that something x. So actually we are talking about g dash of y, but y is nothing but f of x, because every y is of the form f of something, because j is nothing but f of thing. So finally we get in terms of y is f dash x is nothing but you have to take the inverse. So from this, what is x? So y equal to f of x. From this, x equal to f inverse of y. But f inverse is nothing but g, that is g of y. That's why I am replacing x by g of y here. So this is very important. Suppose if you know the inverse of the function, the derivative is the formula. So this is a formula for derivative of the inverse function. So another thing is Cauchy mean value theorem. So in the mean value theorem, we discuss about only one function. So the generalization of Cauchy theorem is the Cauchy mean value theorem. Suppose we have two continuous function on closed interval a comma b and differentiable on open interval a comma b, then what is the Cauchy mean value theorem says? Just a extension of generalization of mean value theorem we call Cauchy's form of mean value theorem. Cauchy's form of mean value theorem, MVT. Okay. What the theorem says, suppose we have two functions. So let f and g, we have two functions from closed interval a comma b to r. And these two functions are continuous and differentiable. So therefore, is better we assume differential, because every differential function is continuous. Suppose we have a two differential function, assume that the derivative of g is non-zero. That is g dash of x is non-zero for all points, for all x in the domain. Sorry, open interval, because differentiable on the open interval. Then there exists c in open interval a comma b. Then there exists c in open interval a comma b such that f of b minus f of a by g of b minus g of a equal to f dash of c by g dash of c. So this is a Cauchy mean value theorem. So if we take the particular case g of x equal to x, identity function, you will get the Cauchy theorem. Sorry, you get the mean value theorem, because just to take what is the derivative of g of x is always 1. Okay, if we take any point, therefore the left hand side we get only the f dash of c divided by 1, and this is f of b minus f of a. But what is g of b? B, and this is g of a is a. Therefore, you can cross multiply, you get gb minus a. So if you take g of x called an identity function, the Cauchy mean value theorem, you get the mean value theorem. Okay, that is a special case. So mean value theorem is a special case of Cauchy mean value theorem. You take g of x equal to the identity function. That is a very important thing. So there are so many problems are there. Just to go through it, you can easily you have to apply the mean value theorem and Rolle's theorem, Cauchy mean value theorem repeatedly. Okay, maybe if possible we will discuss some more examples. So there are Okay, anyway, just to go through the books, you just try to solve the problem, and then if you have any doubt in that, so you can ask. Okay, anyway, I can stop now. Thank you.